I will be starting a series of videos of how to find Legendre's equation using a power series solution method. And today we will be focusing on finding the recurrence relation, because finding a solution to Legendre's equation can be quite long, which is why I'm separating it into multiple videos. So Legendre's equation is a differential equation written in this form, where k is an arbitrary parameter. And the way we solve this differential equation is by assuming that our solutions have the form of a power series. But before we can use the power series method, we need to make sure that the coefficients associated with our differential equation are analytic. So we need to write our differential equation in standard form, and therefore we need our coefficient associated with y prime prime, y double prime, to be equal to 1. And how do we do that? Well, by dividing by 1 minus x squared. So we have y double prime minus 2x divided by 1 minus x squared, y prime plus k divided by 1 minus x squared, y is equal to 0. Now, from this form, we can see that the coefficient p of x and q of x, they are analytic about the point x is equal to 0. Indeed, we can see that because the denominator does not turn to 0 when x is equal to 0, because we have 1 minus 0. So we can see that, we can infer that the coefficients p of x and q of x are analytic at x equal to 0. Knowing this, we can now use a power series solution to solve this equation. And therefore y, we can write it as the infinite series of n, starting from 0 all the way to infinity, of Cn x minus x naught, but in this case x naught is equal to 0, therefore x to the power of n. And our goal is to try to find this coefficient Cn via a recurrence relation. I've written down y and its derivatives in terms of the infinite series. And now what we need to do is plug in these power series into our initial differential equation. We can also plug in into this differential equation over here, so the standard form, but it will be more complicated to do some algebraic manipulations because here we have fractions, and our goal is to try to absorb these coefficients into the summation sign in order to get a recurrence relation. So it's better to operate with our original equation. So I want to emphasize on the fact that we only use the standard form of a differential equation in order to determine the ordinary points related to this equation. So to determine whether p of x and q of x are analytic about a certain point, the ordinary point. So I've replaced y in terms of its power series into this differential equation to get this long expression over here. And now we absorb these coefficients into our summation. So what I've done here is I've distributed the 1 minus x squared into the summation. And note that x squared times x to the power of n minus 2 is x to the power of n, which is what we have here. And I've also distributed the x into the summation to get x to the power of n over here. And so the key part of using a power series is now to have the same index, x to the power of n, on each summation. Notice here we have x to the power of n minus 2, but we want x to the power of n. In order to put this whole expression, all these terms, into one single term with a single summation. So what I've done here is I've shifted index in order to get n equals to 0 and x to the power of n instead of x to the power of n minus 2. And now, in order to compress everything into a single summation, we need to factorize by x to the power of n. But before we do that, we need to make sure that the index over here is the same everywhere in each summation. Notice here that I can set n is equal to 0 in this summation, as well as this summation, because it doesn't change the value of this series. Indeed, if we set n is equal to 0, we will start with n, which is 0, times n minus 1 times cn x to the power of n. But since we have a 0 term over here, the summation starts with 0. And similarly, when n is equal to 1, we have 1 minus 1. And so the value of the term will be 0 as well. So if we set n is equal to 0 in this case, it doesn't change our summation. And same thing here. So I've simplified our expression by factorizing by x to the power of n. And then what I've done here is I've written down cn plus 2 times n plus 2 times n plus 1 coming from this power series. And then for these three power series, I've factorized by c of n in order to get this expression. And notice that we can rewrite n times n minus 1 plus 2n as n squared minus n plus 2n, which is just n squared plus n. And therefore, n times n plus 1. And we require that this whole term be equal to 0. X to the power of n is not always equal to 0. It is equal to 0 only if x is equal to 0. But since x is any variable, well, we require that this term be equal to 0. And this is where we get the recurrence relation from. And so since this whole term needs to be equal to 0, we get this expression. And therefore, we get our final recurrence relation, which is that cn plus 2, c of n plus 2, is equal to, divided by n plus 2 times n plus 1, we get n times n plus 1 plus 2n minus k divided by n plus 2 times n plus 1 times cn. And so this is our recurrence relation right here. And so what I will be doing in the next videos is finding the series solution to this differential equation and also analyzing the radius of convergence of the series solution. And that is it. Thank you for watching this video.